In this video, we will learn about a machine learning model called support vector machine, and we will examine the coding files directly. In this figure, let's assume a two-dimensional space with two different classes. If we can find a decision boundary that can distinguish between these classes, we can classify them. In 2 dimensions, the decision boundary is a line. In 3 dimensions, it is a plane. And in higher dimensions, it can be a hyperplane. There can be many hyperplanes that can classify the classes, so we need criteria to determine which one is the best. The data points that are closest to the decision boundary are called support vectors, and the distance between the hyperplane and the support vectors is called margin. The wider the margin, the higher the probability of correctly classifying the classes. Therefore, the support vector machine model aims to find a hyperplane that maximizes the margin. In the support vector machine model, when we can separate the data linearly, it is called hard margin SVM. When linear separation is not possible, it is soft margin SVM. In the case of soft margin SVM, when we achieve linear separation, the criteria are applied flexibly to allow some outliers to be included within the margin. It's important to note that if we make the criteria too flexible, the classification accuracy may decrease. Therefore, we need to maximize the margin while simultaneously minimizing the margin errors. In this context, the Greek letter xi represents how much allowance we give for data points to be inside the margin. We can control this through the hyperparameter c. As shown here, the Greek letter xi, which represents how much the data points are allowed within the margin, is influenced by the value of c. When c is large, xi becomes small, and the margin is formed narrowly, resulting in lower training error but a higher probability of overfitting. On the other hand, when c is small, case I becomes large, and the margin widens, leading to higher training error. Consequently, the probability of underfitting increases. In a support vector machine model, one of the hyperparameters that needs to be controlled is the gamma parameter, which adjusts the range of influence on the decision boundary for each training data point. When gamma is large, it has a significant impact on the decision boundary for each data point, resulting in a complex decision boundary that can lead to overfitting. On the other hand, when gamma is small, the influence on the decision boundary for each data point becomes smaller, resulting in a smoother decision boundary that can lead to underfitting. When it's not possible to separate the data with a linear boundary, transforming the data into a higher dimension can help in finding a decision boundary. For example, if we have data points arranged in 1 dimension, like x, we can transform them into 2 dimensions using the square function. This transformation may enable linear separation. Assuming that the value of p is less than q, we can use a kernel function to map the original data in the p-dimensional input space to a q-dimensional feature space. Even if we don't know the specific form of the function being used, we can use kernel functions, which allow us to transform data into higher dimensions without complicated computations. This technique is known as the kernel trick. In other words, as shown here, in a 2-dimensional space where data points cannot be separated by color, we can use a kernel function to transform them into 3 dimensions, enabling linear separation. Since the kernel function is a hyperparameter used in support vector machine models, you can try different types of kernel functions such as linear, polynomial, sigmoid, and Gaussian. After trying them out, you can choose the one that shows the best performance. Support vector machine can be used for both classification and regression tasks. As we have summarized so far, it determines a hyperplane that maximizes the margin for classification purposes. Therefore, having a larger margin is better, which is why using a soft margin is recommended. On the other hand, for regression tasks, the goal is to create a line that represents the data. In this case, we aim to have a margin that encompasses the data points, with the regression line placed at the center. Having a narrower margin is preferable as it helps to better represent the data. Hence, using a hard margin is recommended in regression tasks. This slide presents a screen for coding the support vector machine model. The Jupyter Notebook file for this code is available on GitHub, so you can download it and run it yourself. Similar to the previous artificial intelligence models, you need to import the necessary libraries, such as NumPy, Pandas, and TrainTest-Split. Then, you load the dataset from an Excel file. After that, you assign the X and Y variables and split the data into a training set and a test set, with a ratio of 8:2. To build the support vector machine model, we import the SVC library. As mentioned in the previous file, if you encounter an error stating that the library is not available, you can install it using the pip install command. After importing the library, we create a support vector machine model with a linear kernel, a C value of 10, and a gamma value of 1. We store this model in the variable named SVM. As explained in the previous slide, the kernel, C, and gamma are hyperparameters that can be adjusted. Next, we train the model using the X training and Y training data and evaluate its accuracy. The training accuracy is calculated to be 97.5%, and when applied to the testing data, the accuracy is 0.967, indicating that the model predicts the iris flower species with an accuracy of 96.7%. Lastly, we can use the for-loop command to create a simple code that checks whether the predicted flower species matches the actual species. As shown in this slide, when the actual and predicted species match, it is represented as true, and when they don't match, it is represented as false. The code demonstrates that the model correctly predicts the flower species.